All right, so chapter 21 is, I think, the beefiest chapter in the book, in my opinion. It should be split up into multiple chapters, and it is in a lot of books, but he kind of clumps carboxylic acids and anything with a similar oxidation state all into one chapter. So this chapter is not just carboxylic acids. It has to do with anhydrides, acid halides, esters, and amides, and nitriles, and you name it. So we're going to spend a fair amount of time on this chapter. But for the beginning, we're going to focus primarily on carboxylic acids. And let's do a little bit of nomenclature. The nomenclature is pretty straightforward. So let's say we've got this one. First thing you want to do is identify the longest parent chain as normal. And where do you think the number 1 should be? Should it be on the left or the right? Right. So the same rules are followed that we saw before. So this has a hexane parent. And then what we need to do is put that first. So we do hexan. We don't have the ane. And then we change the suffix to an oic acid. So hexanoic acid would be the name of this carboxylic acid. It's pretty straightforward. You don't have to include a number in here, and why is that? Yeah, it's similar to an aldehyde, right? An aldehyde, by definition, will be at prefix 1. When you run into complicated molecules that, let's say, have both carboxylic acids and aldehydes and maybe other functional groups, then it gets really complicated to know what's higher priority. And that's when I would go back and refer to the sheet that I gave you last chapter, where you have these IUPAC priority lists, but carboxylic acids are always going to be the highest priority. If you do have something like an aldehyde coming off, then you've got to use some kind of odd terminology. You would call it a formal group and treat it as a substituent coming off the parent chain. It does get complicated though, and typically I don't test you guys on that. Okay, so let's go back and talk about other IUPAC names, because there's a lot of non-standard IUPAC names for carboxylic acids. So let's start with the simplest one. A lot of people would say, well, is this methanoic acid? People would look at you funny if you said that. Most people would call this formic acid. So like formaldehyde, but with the carboxylic acid on one end.
What ant? Just acid ants.
Exactly. If you've ever smushed an ant and then smelled your fingers, you've smelled formic acid. It smells very, very pungent. The next one is 1 carbon longer. Some people would be tempted to call this ethanoic acid, but again, people would look at you funny if you said that. Does anybody remember what this is called? Acetic acid, vinegar. So acetic acid is very, very common. This one, people would oftentimes call it propanoic acid, which is fine. However, a good chunk of people will still say that it's not propanoic acid, it's propianoic acid. I'm fine with it either way for that one. It doesn't really bother me. This next one is super duper smelly. This is called butyric acid. Has anybody seen the show Whale Wars on the Discovery Channel? So the whole show is about Japanese whaling ships going down to the Arctic, and they're claiming that they're hunting these whales for research purposes. However, that's a very dubious claim. And so this whole organization that's a little left of center, so to speak, goes out there and tries to harass them so that they can't catch as many whales. And what they do as a non-violent way of protesting is they take bottles of butyric acid and they throw it at the ship. Not only does that spoil the whale meat, but it is like the most intolerable smell you can be around. If you've ever vomited, imagine concentrating that smell down, putting it into a bottle, and then throwing it at somebody. That's what butyric acid smells like. It is rancid. It is really bad. The next one, you guys already know the name of. What's this one again? Benzoic acid. And then this one's kind of an oddball one. This is cyclohexane carboxylic acid.
Not cyclohexanoic.
Yeah, I don't know why they don't call it cyclohexanoic acid, but it's just not called that.
The one that you use more ink when you have to type it on a paper.
Yeah, exactly. There's also a bunch of diacids where if you go on and take biochemistry, you'll see them regularly. So I do feel like I have to show you guys the nomenclature for that. And a diacid is a simple compound that contains two carboxylic acid groups. So this one's the simplest. It's got two carbons. This is called oxalic acid.
It's a radiator cleaner.
Is it?
I think that's what they use in the radiator.
It's used a lot in cleaning. I think it's a nice gentle acid. The next one has one more carbon on it. This is called malonic acid. And then we'll go down the list. This is called succinic acid. It has 4 carbons on it. And we'll keep on going.
There's no system to this.
I'll show you guys a cool trick though. This is glutaric acid. Next one, we've got one more carbon. So that's 2, 4, 6. What's the name of this one? Adipic. We made this in second term. And then one last one, and then we'll stop. So 1, 2, 3, 4, 5, 6, 7 carbons. This is pimalaic acid. As you guys can see, there's no rhyme or reason to the naming system. This is all holdover naming conventions before IUPAC was invented, but I'll show you guys a good system for memorizing this. And it's a simple phrase. Oh my, such good apple pie. So first letter for the 2 carbon one is O, second one's M, S, G, A, and P. This got me through grad school. You guys can remember this. So anytime you forget the name of a diacid, just remember the mnemonic, oh my, such good apple pie. All right, one kind of odd thing with carboxylic acids is their hydrogen bonding. A lot of people said when they made their benzoic acid that they had a hard time getting it dry. Normally we would let things dry in our drawer for a day and it was perfectly dry, right? With the benzoic acid, it was clumpy, it retained water for a long time. That has to do with the strong hydrogen bonding nature of carboxylic acids. They really, really like to form dimers with one another, and they like to hydrogen bond onto other hydrogen bond donors or acceptors. So let's compare these two. You can see that you'd have a really strong hydrogen bond between the oxygen and hydrogen there, and then another one here. So they really like to dimerize. The pKa of most carboxylic acids falls within the 0 to 5 region. I'm going to say approximately 0 to 5, which is a pretty big range for a functional group. Why does it have such a big range? What can affect its pKa? Yeah, resonance. So benzoic acid has a very different pKa than something like acetic acid. So resonance plays a big role. What's another thing?
Could be the size of the molecule too.
So potentially size. Size?
I think the rest of the R bond there.
Yeah, so size does play a role with pKa, although arguably it plays a pretty minimal role. That has more to do with solvent accessibility. So resonance is a big one. Size is pretty moderate. What's another one? Induction. So trifluoroacetic acid is really acidic compared to acetic acid. Those fluorines can really change the acidity of that carboxylic acid group. Okay, so what we have to do now is a bunch of review. Oh joy. And then we'll start going into new mechanisms. So let's review preparation of carboxylic acids, and I want you guys to help me fill in the arrow and then check with your neighbor. So I'll make a list and you guys help me out. All right, one last one, and then we'll do the review. All right, let's do the top one first. How can we go from a primary alcohol to a carboxylic acid?
Chromic acid.
Chromic acid. So chromic acid, we typically have to make, so using sodium dichromate. So Na2Cr2O7, H2SO4, and water. It's not a very green reaction, but if you want to review it, it's in section 10.9 in your textbook. It was a reaction from second term. All right, the next one. How can we go from toluene to benzoic acid?
KMNO4.
Or chromic acid.
Or chromic acid. So the most common one is KMNO4, NaOH, H2O, and heat. That was what we saw on the exam, followed by an acid workup, which was missing on the exam. And this was section 18.6 in your textbook. So again, a reaction from last term. And then how can we go from an internal alkyne to a carboxylic acid? Ozonolysis, so ozone and water. Does this work only with internal alkynes?
You'll get a mixture.
Yeah, you'll get two different carboxylic acids depending on the identity of the R group if it's non-symmetric. But what if it's a terminal alkyne? Does it still work?
Then you get CO2.
Yeah, you can bubble off CO2. So it does work with terminal alkynes too. All right, how can we go from a nitrile to a carboxylic acid? We saw this briefly last term,
Acid.
or last chapter.
Acid and water.
Yeah, acid and heat.
Oh,
And this is actually related to your pod. It's really similar chemistry to what we saw last chapter, so trust your gut and make sure that when you're doing proton transfers that you're following the same set of principles. So acid and heat. All right, then the last one. How can we go from benzaldehyde to benzoic acid? Peroxy acid, so RCO3H. This is an example of the Bayer-Villiger oxidation. And then last but not least, let me fill this in. That was covered in 10.9. And then this was from last chapter. All right, there's one last cool method we have for prepping carboxylic acids that we haven't covered yet. One more thing for your reaction map. This new method is actually pretty clever. First thing you do is you get a Grignard reagent. You huck in some dry ice, so CO2. And then at the end you quench it with acid. And you can go straight to a carboxylic acid this way. What's one potential pitfall? Does anybody want to identify a pitfall? What else can Grignards do? They could add into other like ketones, esters, aldehydes. They can do acid-base chemistry. Grignard reagents are pretty dang strong nucleophiles, so you got to watch out for any other chemistry. Typically, this is only done if you have an R group that is completely unreactive towards Grignard reagents, right? So watch out for that. This isn't a foolproof way, but it's a pretty clever way. And let's take a look at the mechanism. This mechanism is very intuitive. If you remember, I said you could draw a Grignard two different ways. You can draw it covalently bonded between that R group and the magnesium, or ionic. It really doesn't matter. It's a very, very strong dipole. And then we're going to react this with CO2. Where this Grignard reagent, is going to attack this carbon and kick up electrons onto the oxygen. Giving you your carboxylate salt. And then last but not least, you're going to treat this with your acid in order to neutralize your carboxylic acid and give you your final product. Does that make sense? Pretty nice workaround, especially if you've got a way of installing a bromine. That means you've got a direct way of converting that bromine into a carboxylic acid. All right, now we've got to do reactions of carboxylic acids. So we did preparation, now we've got to see what they do. And again, a lot of this is going to be review. So we'll go through it pretty quickly. What if I want to do the reverse reaction of going from a primary alcohol to a carboxylic acid? What reagent would I need? LAH. So lithium aluminum hydride, followed by an acidic workup. Why can't I do this all in one flask? Why does it need to be two steps? Yeah, it's a super strong base. LAH would deprotonate your alcohol, so you actually have to run it in a polar aprotic solvent and then separately protonate it. We talked about the mechanism with aldehydes and ketones, but we really didn't do it with carboxylic acid. So what we've got to do is go back a little bit and talk about this mechanism. Because it is a little bit different. So like I said, lithium aluminum hydride is a much, much stronger base than sodium borohydride. So the first step is going to be the fastest reaction in chemistry. It's just going to deprotonate your carboxylic acid. And then this next step is kind of interesting. The aluminum is actually going to, the hydride is going to attack in. This pi bond is going to kick up, and then the oxygen is going to attack the aluminum. So it goes through this funky pathway. Yeah, it does seem counterintuitive, but I'll show you why there's evidence to support this. So now we've got this complex. The reason we think it goes through this pathway is at this point, this is a pretty good leaving group. If all it did was the deprotonation, it would be dead in the water. So if that's a good leaving group, what do you think happens next?
Lone pair comes down from the oxygen.
Yeah, the lone pair comes down from the oxygen, and this clamps down. Which results in an aldehyde, right? At this point, though, it's really, really, really hard to stop at the aldehyde because it's even more reactive than your starting material. So usually this reaction is done with an excess of lithium aluminum hydride, where the next step involves another addition of hydride. Followed by your acidic workup. And there you go. Oftentimes these aluminum salts are really hard to remove, so if you ever are in lab and you have to do these, there's a very special extraction technique for removing the aluminum salt. You typically have to use another salt solution called Rochelle salt in order to help purify this. However, I don't think we're ever going to get a chance to do this reduction. There is an alternate technique that's also used for reduction. If you have a carboxylic acid, you can treat it with boron THF. And go directly to your alcohol. We're not going to go over this full mechanism. However, it is pretty similar to the aluminum one. So you're going to convert it into a good leaving group and then reduce it from there. The neat thing with this is that this only works for carboxylic acid. So it's not universal. And this can be handy sometimes. So let's imagine this example. Let's say we treat this molecule with boron THF. The ketone's just going to stay put. Nothing's going to happen to it. And we can reduce the carboxylic acid to an alcohol. So now we can selectively reduce either a ketone or a carboxylic acid without touching the other. It's a nice workaround. There's also the one we saw on our last exam. Where you can use carboxylate salts as nucleophiles. This is a pretty simple application of carboxylic acid reactivity, where if you take a carboxylic acid, you treat it with sodium hydroxide or any other base, you've got this carboxylate salt. Am I spelling that right?
No, you've got the carboxylate.
There we go. Sorry, my brain's kind of mush. All right, and then in the next step, you're somewhat limited, but this can work. You can treat this with an electrophile, and you can convert your carboxylic acid to an ester. However, this electrophile must be good. Why is that?
Sterically hinders your
Yeah, your nucleophile is sterically hindered, and what else is bad about it as a nucleophile?
Resonance, it's pretty stable.
Yeah, resonance, right? So that negative charge is delocalized across both oxygens. Carboxylate salts aren't very good nucleophiles, but if you've got something like methyl bromide or methyl iodide, it's good enough. So typically, if you're forming an ester, you're pretty limited. It works well for things like methyl esters in particular, but once you get into higher level esters, it just doesn't work very well. Does that make sense? So let's review from first term a little bit. All right, so that's kind of the carboxylic acid section in a nutshell. We'll go back and do more reactivity with it. But the rest of the chapter is focused primarily on carboxylic acid derivatives. And I'll show you guys why he lumped this all into one chapter. Okay, what's the oxidation state for the carbon in a carboxylic acid? +3, right? So if you're rusty, remember that the more electronegative atom gets all of the electrons, and then if you're an atom that's equivalent, then you share them, right? So in this case, it really only gets one electron from this bond. It normally has a valence of 4, so 4 minus 1 is +3. The same thing is true for any electron withdrawing group coming off of that position. So all of this chapter focuses on carbonyls where you've got a carbon that has a +3 oxidation state. But let's take a look at the various electron withdrawing groups that would fall into this category. +3 carbons. Okay, so the first one that we've got is an acid halide. So the X can be usually chlorine or bromine. Why don't we have an iodine on there?
It's not strong enough.
It's actually such a strong acid halide, it falls apart if you look at it funny. I can show you guys a paper. However, the 99% of acid halides that you'll see involve chlorine and bromine. If you throw in elemental iodine, or iodide I should say, you can actually form a trace amount of the acid iodide. However, it's present in a tiny, tiny, minuscule quantity. It is a neat workaround, though. Okay, so those are common. And let's see if you guys can remember this functional group. What's this one called? Anhydride. Some people will call this an acid anhydride or an anhydride. It doesn't really matter. So if we look at these, the X is our electron withdrawing group here. This is our electron withdrawing group down here. Okay, if we keep on going, we've got our esters. Again, we've got this nice electron withdrawing group. And keep going. This could be any sort of amide. It really doesn't matter, as long as there's that nitrogen attached to the carbonyl group. And then last but not least, what's this functional group called? Nitrile. You can call it a cyano group if you're treating it as a substituent, but most people would call this a nitrile. And again, this is simply due to that nitrogen being electron withdrawing. All right, so if we look at these have a very specific order of reactivity where we get more reactive going up. Does anybody have an idea why?
They're stabilized and
Yeah, so if we look at the thing circled in green, if you imagine it falling off with a negative charge, halides are really stable with a negative charge. The anhydride, you'd have something like an acetate as a leaving group. Yeah, that's got resonance stabilization. That's pretty good. Esters, a little less so. They don't have that resonance. Amides, pretty crummy leaving groups, and then nitrile is definitely a crummy leaving group. However, the neat thing is we can interconvert between a lot of these. The number one piece of advice I would give you guys for this chapter is really, really, really focus on these guys, because these will give you access to the biggest variety of functional groups. You can interconvert between an acid halide to an anhydride to an ester to an amide to a nitrile very easily. Whereas if you're in an amide, it's a lot harder. You're a little less able to interconvert. All right, so I think we've got, I don't know if we'll have enough time. How about we just cut it off there, and if you guys want to get started on your pod, you guys are welcome to get started.